All right, so this is week 12. We're going to be looking at the first problem, 14.65, in which air enters a 30 centimeter cooling section at 1 atmosphere, 35 degrees Celsius, and 45% relative humidity at 18 meters per second. Heat is removed from the air at a rate of 750 kilojoules per minute. We are to determine the exit temperature, the exit relative humidity of the air, and the exit velocity. Okay, so what we're looking for is what is the velocity G over here, temperature G, or dry temperature in other words, what is the relative humidity on this end here. We know that air is coming in through this side over here. It has some velocity, and we know there's a coil there that's removing some heat. So whatever the entropy, the energy, right, the entropy on this end here, we know that the entropy on the other end has to be what? Has to be smaller than the initial one, right? Because we were removing part of that energy there. Okay, what else we know? We know that all the properties related to these psychrometric charts are related, right? So there's two ways we can solve this. One is using the actual psychrometric charts and reading off of it. The other one is using online tools that just spit out the output of the situation that we have. Okay, what does that mean? What do I mean by that? I mean that as long as we have two properties, right? In this case, we have on the entrance, we have the dry air temperature and the relative humidity. So as long as we have two of those, we can grab all the other properties related to this. So we can grab the enthalpy, we can grab the specific volume, we can grab the specific humidity, right? So the amount of water that we have in here. So as long as we have two of these properties, we can define the whole state. Now on the exit side, right, on the right hand side, on the part number, state number 2, I need two properties to be able to relate all these things that that are being asked in the problem. Now, one of the things you can imagine is going to be the enthalpy, right? Because we can relate the energy that we have initially, and then the energy that's being removed, and calculate the end enthalpy, right? The final enthalpy. And the other thing is to note that what's being removed here is being removed by this 750. So this arrow here is removing heat, right? It's really Q, and that's in heat rate, and it's the rate of heat, 750. But this is heat, this is not mass, right? So whatever the mass of water is here on the entrance, right, because mass cannot be created or destroyed, has to be the same amount of mass that we have on this end here, right? So that means that the actual quantity of mass that we know is going to be the specific humidity, right? Specific humidity, also called absolute humidity, right? Specific humidity or absolute humidity has to be the same. So whatever omega is on the left side has to be the same as omega on the second side. So as long as we can find the enthalpy H2, we can combine those two things to find all the properties that we want for the right-hand side. So I'm going to show you guys how to read it off the chart. But I've been thinking about it. This is quite interesting because of the situation that we have. You guys are at home. The exam is going to be open book and it's going to be at home. I don't think it's worth spending much time on the psychrometric graphs other than just to explain to you how they work so that in case you guys ever need it. Because as long as you have a computer with you, you can grab these properties using the computer, which is much easier. Okay, so let's have a look at the things that we have. Let's define the whole state, and then we can talk about how to use a computer and how to use a chart. Okay, so my initial states, state 1. On state 1, I know that we have the relative humidity, 45%. We have the dry bulb temperature as 35 centimeters degrees Celsius. And so we have relative humidity 1 is 45%, and we also have T1 at 35 degrees Celsius. We also have the velocity of that air coming in. We can deal with the velocity later because part C is asking us for the velocity, so we can use mass conservation for that. For now, let's just try to figure out what's the temperature and the relative humidity on the state 2. Okay, so I'm going to jump into the psychrometric chart. You can find them on the same property table. They're also going to be there. It's going to be A31 on page. I don't page it. A31. Let's look up on the property table. Let's open it up here. Just going to share this guy. So this is the psychrometric chart. What do we need to know about this guy here? We need to know that on the bottom right, so on this bottom side here, right, on the x-axis, I have the dry bulb temperature. And the dry bulb temperature is pretty much, you can think of it as the temperature of the system, right? So the temperature of the air in which we have the combination of air and water. That's the temperature of the air. The dry bulb temperature. That's the main temperature we're going to be usually concerned with. Okay. Now, you can see we have heaps of information here, and the idea of this psychrometric chart is that they're all related. Okay. So long as I can find one, I can place this guy on one part of the graph, so I can place myself here, that means I can grab all the properties from this chart. So that means I can go follow this dotted line here, and I can go all the way here and grab the enthalpy. So in this case, my enthalpy will be 42 joules per kilogram. I can also grab the temperature if I wanted to. So I can go down here and grab the temperature, dry bulb temperature over here if I wanted to. I can grab the relative humidity. It's going to be 40% on this point here. Right? That's the screen line over here. What else can I grab? I can grab the saturation temperature. So following the same line that we did before, going in this direction here, you can grab saturation temperature right there. And these numbers here, 10, 15, 20. And all the way to the y-axis down here, I can have the humidity ratio. So that's how many, that's also known as specific humidity or absolute humidity. So that's how many grams of moisture, so that's how many grams of water I have for every kilogram of air. And so at this point here, just have to go to the right all the way, and I can grab property here off this chart. Okay. What else? A specific volume. So I can read it. This is 0.84 here, 0.86 here. So on this guy here, it's going to be 0.85 meters cubed per kilogram. And here you can see the units, cubic meters per kilogram. Okay, so all these things are related. That's what you guys need to understand from this chart. The other thing you need to understand before I show you the quick way to do this is that this is only valid for 1 atmosphere, right? So atmospheric pressure. Okay, this is not going to be valid if I change my pressure. All these values are going to change. They're all related to pressure, right? So if I have 2 atmospheres, for instance, all these values will change. Okay, so be extra aware of that. It's very important for you guys to understand. Okay, so what you need to take from this is that you can grab all these properties as long as you have 2 of them. You can grab all the other properties. They're all related to each other. And that you can do that using this chart, or you can do this online with online tools or with even Excel and things like that. Now, for the sake of this problem, I'll show you how to do this. I have my Git node paintbrush here. Okay, so on Paint now. On Paint now, I just took a screenshot of that. And I'm going to look for the point that we're looking for this specific problem. So that's relative humidity of 45% and dry bulb temperature of 35 Celsius. Okay, so we have 30 down here, 30 Celsius, and 40 here. Right in the middle, that's going to be 35. If I have this left up here. Okay. So if I follow this guy here, grab shift handle straight line. Okay, so if I do this straight line up here, okay, my state will be somewhere along this blue line that I just drew. And then the other thing is 45% relative humidity. So this is 40%, this is 50%. It's going to be somewhere between these two. Okay, that's why I have these red parts here. So it's going to be between these two lines here, somewhere on the red one. So if you count here, we have 1, 2, 3, 4, 5, 6.5. Let's just count 3.5, 1.5, 1, 2, 3. Okay, so somewhere along these lines here, will be my input. Okay, so here, probably the values, probably here is the middle. 1, 2, 3, 4, 5. And probably this one here. One straight line. Okay, so what I'm doing is I'm following this slope here, instead that we have on the chart here. I'm trying to follow it all the way down until I hit the point that I want. So I can read off what's the entropy of this state. Okay, and then reading off this guy at least having 1, 2, 3, 4, 5, 6, 76 kilojoules per kilogram. Okay, I can also grab my specific volume, which is going to be, so this is 0.9, this would be 0.89, so it's going to be between 9 and 0.89, so it's 0.895. Okay, but what I want you guys to see is that I can grab obviously approximations to these guys, right? So I'm doing 0.89 from this guy and 0.1 from this guy. And the two kind of falls, this point that we have here kind of falls in the middle. And that's why I'd say 0.895. But all these are obviously approximations using this psychrometric graph. And then if you have this guy on paper, you can use a ruler and then you can find this better. On the computer, I honestly find it pointless for you guys to do this because you can grab specific ones and precise ones using an online tool. Okay, so if I were to continue this problem on this problem using the values that I'm grabbing off this chart, I'll grab 76, was it? And we just found 76. So my entropy would be 76 joules per kilogram, and my specific volume is 0.895 meters cubed per kilogram. And I can write those things as state 1, and then I can use the entropy to find state 2, right? And I can also grab the how much amount, the amount of the omega, right? So the amount of water that I have for every kilogram of air. But now I want to show you the method that I think you guys should be using, especially in coronavirus classes. Okay, so I have an online tool here. You guys can find anyone that you want. Okay, you can find anyone that you want. This is just one that I found online. You can grab the website. It's hvac-calculated.net. And on this guy here, what I'm going to do is I'm going to put 2 properties. So there's all these properties. I'm going to put 2 of them. And when I hit calculate, it's going to spit me out all the other properties because they're all related. So what this guy is doing is it's reading off the diagram, right? It's reading off the diagram, the related properties, and getting this back to me. So in our case, we have 2 things that we have relative humidity. So this guy here is 0.5. And we also have the entropy. No, not the entropy. We have temperature. Variable temperature, 35. Okay. So when I calculate everything else, so these are all the values that you would get off the chart. Obviously approximating, but this one is precise. Okay, so for instance, the entropy is 76.1. You grab 76, so you weren't that much off. The specific volume, however, is 0.9, not 0.895 that I said before. The amount of the absolute humidity or specific humidity, that's 0.059 kilograms of water for every kilogram of air. So that's equivalent of saying this is 15.9 or 16 grams of water for every kilogram of air, right? The important thing is that you can grab all the properties that you need to be able to continue this. So I'm going to grab these values. I'm going to grab these values from this calculator here, and I'm going to place it in our whiteboard. So let me go ahead and share the whiteboard again. Okay, so we're back here, and I'm going to put down the values that we got from the calculator. So we got from the psychrometric chart. Okay, either yourself or using a calculator, you can now have omega 1. That's the amount of water that we have, grams per kilogram of dry air. So it's the amount of water that we have, 15 kilograms, 15 grams of water per kilogram of dry air. We also have the what was it? 76.1 joules per kilogram. We also have a specific volume 139 meters cubed per kilogram. That's the only thing that we need. You can also grab the dew point, you can grab the wet bulb temperature if you want to, but you don't need it. Right, so we have state 1 completely defined, and now we can try state 2, because we know a couple of things about state 2. Right, as we talked about before, on state 2, we're not changing, the coils aren't removing water, right? So whatever the amount of water that we had before, those 15 grams have to be exactly the same 15 grams of water at the end of it, right? We didn't remove any water. The mass conservation says it has to be the same. The other thing that we know is that the amount of enthalpy, right, the change in 700, this way, the amount of Q removed, Q out, has to be equal to the difference in enthalpy, right? And we know the second one is going to be smaller, but the only problem is that we have the removal of heat in power, so we're going to have to multiply this by the mass flow rate to have this in power as well. So if we had the mass flow rate, we could go ahead, but we don't. So let's find out what's the mass flow rate that we do have. We just grabbed the specific volume. We know the velocity and the area, right? So it's a little two. We know this guy has a diameter of 30, was it? 30 centimeters? Yeah, 30. This is 30 centimeters. It's coming in at 18 meters per second. So that means that we can calculate the area first. That may be this guy here, this here. This area is here. So it would be 30 times 10 to the minus 2 to have this in meters. So let's use squared area. And we can calculate our volume flow rate, right? You know, our volume flow rate would just be the velocity times the area. In this case, it would be 18 times 5 is 30 equals 2, 2 squared, which gives us approximately 1.27. Okay, and why did I do this? Because now that I have a mass flow rate, this is extremely convenient because I can combine this information here with this information over here and find my mass flow rate. Because we know that in red, we know that our specific volume is nothing more nothing less than that volume divided by mass. So if we take derivatives on both sides, we know that specific volume does not change with time. So that means we can do specific volume is something like the volume flow rate over the mass flow rate. So in this case, if you want the mass flow rate, you just need to take the volume flow rate and divide by specific volume. We have more from those guys, 10.27 divided by 0.9. And what did I get? 1.42. Okay. Now with that mass flow rate, I can go ahead and calculate what will be the H2, right? Now, as I always tell you guys, there's two ways you guys can go about doing this math here. So this point in math here, you can go about this. Okay, let's do both so that nobody's unhappy. Okay. First way is okay. I don't like to deal with negative values. So I'm going to notice that my state 1 is over here, and my state 2 is down here. Right? So I know I'm removing energy as a different one together. We got 750. Right? So because I know that, I'm going to do it for the 750. We'll do, if you look for that, we'll do 4 minutes. We'll do 10 minutes, which is I'm going to go ahead and do 1 minute 67. So I can remove that benefit. So this guy has to be equal to the difference in energy, and I know one has to be greater than 2, so I'm going to be H1 minus H2 times my mass flow rate. Okay, that's one way to set up the equation. The other way is, you guys like moving the other way, you can do, okay, since this energy is 750, since 750 is leaving, it's going to be negative. So therefore, it's going to be negative 750 is a conversion to second. Has to be equal to the end state minus the initial states, right? So it's going to be like H3 minus H1. Okay. Note they are both going to be whether the same result for H2, right? The difference is that you don't have to account for this negative value here. Up to you. What do you choose to do? They're both correct. They're both same answer by the end of it. Okay, I'm going to stick with the top one. So in this case here we have 12.5 divided by the mass flow rate, which is 1.51, has to be equal to my 1.2 equals the, what was it, the 76.1. It's 806 minus 76.1. That's 67.2. So therefore, which is 67.2. Cool. Now we have two things for state 2, right? Because we know, let's go back, have a look at what we have. We know that so the entropy is 67.2, and we know that the absolute humidity is, what was it, 15.94. So I can go back to my chart. So again, what we do now is with H2 and omega 2, you can go back to my chart. So I can go back to A31, and again, use a chart or use the online tool, and I can grab everything I need for state 2. So let's go ahead and then go back here. Cool. And now this guy is exactly the same in the second state. And the enthalpy, which is the other thing that we have, was 67.2. Calculate. Okay, so our second state has a temperature, T2 of 26.4. It has a relative humidity of 73.5. That's A and B right there. And it has a specific volume of 27. So we can use this to calculate what's the velocity and the output, right? Let's go back. Pretty much notice that we just solved it. We could have done this with the psychrometric graphs as well, obviously, but we just solved it easily. Let's go back here. So with this, the graph of graph T2, the divided 1 is 36.4 Celsius, so that's our final answer for A. Relative humidity 2, so that is 73.5%. So that was B. And then for C, we're going to need this guy here, right? Because we're going to apply some mass conservation. Oops, this is the okay, so for C, first to finish off C, you can do mass conservation. Because we know the mass flow rate and 1 has to be equal to mass flow rate of 2, because we don't have any mass entering or leaving other than from the entrance and the exit, right? So that means that we can, using the same relationship that we did before in red over there, we can transform this. This is the same thing as volume flow rate over this one equals volume flow rate 3 over specific volume 2. And our volume flow rates are again to area 1, velocity 1 divided by specific volume 1, which will be equal to area 2 times velocity 2 divided by specific volume 2. The areas are exactly the same. The sky does not change in diameter as we go through, so it doesn't really matter what that area is. And then you get the relationship that my velocity 2 has to be equal to my velocity 1 times my specific volume 2 divided by my specific volume 1. We have all that right, so that's going to be 18, the initial velocity. Mu specific volume 1087. And my new one is 0.9. Oh, sorry, my original one is 0.9. And just remembering that this is meters per second times meters cubed per second divided by meters cubed per second. Right? So you guys on this one. The way in the left of meters per second, which is the left. Now I got this to be 17.4 meters per second. So that's going to be our answer for C. So what is the, again, reading off the actual question? It read, what is the exit temperature? So the exit temperature of this long diameter section is 26.4 Celsius. Whenever they're only talking about temperature, dry bulb, okay? The wet bulb is not going to be, we have to specifically talk about wet bulb to calculate. B, exits relative humidity of air, so 73.5%, and C, what's the exit velocity? That's still 17.4 meters per second. Cool. Hit me up if you have questions.